that is, of course, we are not saying that the only cause of smoke of cancer is smoking, or we are not, neither are we saying that if you smoke you will definitely get cancer. On the other hand, we are not saying that whenever there is a cloud there will be rainfall, but like there can exist a causal relationship in the sense that if a particular person has cancer, it may happen that that cancer was caused due to smoking. It may have been caused due to other reasons also, but smoking is a possible cause of cancer. So, this statement that smoking causes cancer, this may be a loose statement because it need not cause also. It's possible that someone smokes all through their life, but cancer does not happen to them. Similarly, one can also get cancer without smoking. But so this is an example of a statement which we loosely make, that is which is partially correct but not correct in the true sense, as we will try to understand later. But in general, the idea of causality is that if suppose I say X causes Y, that means Y, that means what? That means if X takes certain values, then Y is going to take some specific values. But if X did not take that value, then Y would probably not have taken that particular value, all other conditions remaining constant. Okay, so that is one way of understanding causality. Now causality can be bidirectional also. Suppose it happens that we have two variables X and Y, and we know that X causes Y, but it may also happen that Y causes X. So if that happens, then like we know, we call that as either a self-replenishing process or a self-destructive process. That is like if X, like it may happen that X equal, like an increase of X results in an increase of Y, and an increase of Y results in an increase of X. So if that happens, that is basically like it's what we sometimes understand by a vicious circle or a self-replenishing process, as I said. So it's like, say, like consider this example. So suppose X is the variable X stands for high temperature, and this variable Y is called rainfall. Okay, so now we know that if temperature is high, then like if the surrounding temperature is, if the ambient temperature is high, then water will evaporate from the different water bodies. Now once the water evaporates, what happens? It forms clouds, and then these clouds cause rainfall. So like when there is high temperature, like after a period of time, we may see high rainfall. So that is, an increase of X causes an increase of Y. But when rainfall happens, then it may bring down the temperature. Okay, so like an increase of Y then causes a decrease of X. So this is basically a self-destructive process. That is, whenever a temperature becomes high, then that causes rainfall, and the rainfall brings down the temperature. Had that not happened, then the temperature would of course go on increasing, and the world would have become an unlivable place. Right? So this is like a natural self-destructive process. Then similarly, there can be self-replenishing processes also. Say for example, again let me give an example from climate domain. So suppose the temperature is X and the carbon dioxide concentration is Y. Okay, so when the temperature becomes higher, that is when the surroundings become hotter, then people start using air conditioners. Now, air conditioner releases carbon dioxide, which we know is a greenhouse gas. So, if there is carbon dioxide released in the air, then that basically does not allow the earth to cool off. As a result, the earth's atmosphere retains some heat. As a result, what happens? The temperature also remains high. So basically, an increase of X causes an increase of Y. Increase of Y causes an increase of X. So this is basically a self-replenishing process where this cycle results in the the temperature getting higher and higher. So like this is, in fact, this is one of the main causes of global warming, right? These greenhouse gases like CO2. So this, it is because of the presence of such gases that the world is getting hotter and hotter. But but otherwise, if it had been the natural process, then like whenever it became, the place became hot, then it would there would be rainfall and it would bring down the temperature also. So like it's a, so here in both of the cases you can see that there is a bidirectional causal relation, like x causes an increase of y and y causes a decrease of x. Here x causes an increase of y, y causes an increase of x, etc. Of course, there are other factors also in between which may change the cycle. For example, this water evaporation, in this case, formation of cloud, etc. These are other variables which intervene between x and y. So it's possible that if some of these variables take some other, like are influenced by some other factors, then this causal relationship may be hampered. Okay, but for like anyways, for the time being, let us just focus on these two things. So it's basically saying that all other things remaining constant, all other factors remaining unchanged, an increase of x results in an increase of y, and an increase of y results in a decrease of x. So we that is so we can say that x causes y and y causes x with a rider, and the rider is that all other conditions remaining unchanged. If some other conditions in the in between changed, say for example that is apart from the rainfall there was some other factor also, then that is even in the presence of rainfall y, the temperature may not have come down, or like or it may happen, say for example, if there is a desert. Okay, so in that case there is no way to I mean there is no water to evaporate. So in that case that is an increase of x also would not have been able to cause an increase of y. So it's like there are other factors coming in which may hamper this causal relationship, but the only thing which we are claiming here is that if all other factors remain unchanged, then x causes y in a particular way and y causes x in another particular way. Okay, so now suppose I have any two variables x and y, and I am interested to understand, can we say that x causes y, or can we say that y causes x, or are both of these true, or are neither of these true? All four possibilities are there. Okay? And typically it may happen that the data may be provided to you in these ways. So x and y. So like if you see, if you take a look at these, the first data set that has been given to you, you may see that here whenever x increases, y increases, x decreases, y decreases, x increases, y increases, x again increases, y again increases, x further increases, y also further increases, x decreases, y decreases. Okay, so here you can, so here in case of this particular data set, what can you say about the correlation between x and y? Yesterday we discussed about correlation coefficient. So now in this data set, if you are given this x and y data set, what can you say about correlation?
So it will be positive.
Positive, and specifically what can its value be? Like will it be 0.05 or will it be 0.3 or
On the
will
higher,
it be,
on the higher end.
yeah, it will be like close to 1. That
Yes.
is because like in fact we see, like in fact it may become like if we focus only on this much, it may become very close to 1, or because that is we see that there is absolutely perfect relationship, that is whenever one is increasing the other is also increasing, and besides by almost by a comparable amounts. You can see that whenever this increases by certain quantity, this also increases by a comparable or nearly proportional quantity, and so on. Now if we look at the second time series, so here let us see what is happening. Here x increases, y decreases, x decreases, y increases. X increases, y decreases, x still increases, this time y also increases. Now x again increases, y again increases, x decreases, and uh, y like x decreases, y increases. Okay, so in this case, this time what can you say about the correlation?
So it will be really less, and it can be either, I guess.
So like if you see, like here you can see that in some cases an increase of x is causing an increase of y. In some other cases it's causing a decrease of y also. So similarly, a decrease of y sometimes a decrease of x sometimes is causing an increase of y. In some other cases it's causing a decrease of y. So if you just calculate the correlation coefficient between these two, we may not be able to make much of it. Now if you look at the third time series, the third data set, here let us see what happens. Here x increases, y decreases, x decreases, y increases, x increases, y decreases, x decreases, y increases, x increases, y decreases, x decreases, y increases. So here it seems it's almost a fine negative relation between two. Whenever x is increasing, y is decreasing. Whenever x is decreasing, y is increasing. So here and it seems a good positive relation. Here it seems a good negative relation, and here it seems no particular relation at all. Okay. So now in the in this case, now let us see one look at one particular aspect of it. So here if you look at here there is an increase of x, here from here to here there is an increase of x, from here to here there is a decrease of x, here to here again it's a decrease of y, here to here there is an increase of x, here to here there is an increase of y, here to here again an increase of x, here to here again an increase of y, and so on and so forth. So that means what? It's like saying whenever x increases, then y increases in the next step. Okay, so in this case, whenever x increases, y increases too, and whenever x decreases, y decreases too. A similar thing in this case also. But here, if you see, whenever it's like when x increases, then y increases in the next step. Now when x decreases, then y decreases in the next step. So here, so yesterday I was talking about like identifying lags in the autocorrelation, right? So like we are talking about comparing a time series against the lagged version of that time series. So here basically, if you consider the lagged version, that is if you are comparing y with a lagged version of x, that is when that is to say, when you are considering this, you are actually like when you are comparing this change of y from 105 to 176, you should, if you like you that is at t equal to t2 to t equal to 3, you are actually looking at the change in x at t equal to 1 to t equal to 2. Similarly, here again, when you are seeing, you are considering the change in y from say t equal to 5 to t equal to 6, here you need to be compare it with the change of x from t equal to 4 to t equal to 5. So it's like there is a time lag in the correlation, but if you take care of that lag factor, then correlation is quite high. So here it happens that both of these, like in this case there is high positive correlation, here there is high lagged correlation, and this is a strange case. Here if you consider a lag factor, then also you will see a high correlation. So you can actually look at the data set again. So here an increase of x, increase of y, from here to here a decrease of x, here to here decrease of y, again here to here increase of x, here to here increase of y. So if you consider the lag in this case, you will see a positive correlation. But if you don't consider the lag, then you see that it's a strong anti-correlation. Okay. So, so the only reason why I am saying is this is that the concept of correlation can often be misleading. Okay, and now in now tell me one thing just based on intuition. In all these cases, in which cases can we say that y is the cause and x is the effect? I am making a statement like y is the cause and x is the effect. So like I am seeing that whenever x increases, y there is an increase of y, or maybe whenever there is an increase of x, there is a decrease of y. Okay, so that is something which I am observing and I can measure it also. But can I say that one is the cause and the other is the effect by looking at the time series? So I am making a statement to you that in all these three cases, y is the cause and x is the effect. So contradict me if you can. Can anyone make a comment?
Right. I think it's true in all the three because whenever y, because if something happens to y, then something happens to x, maybe in the same step or in the next step.
Sir, correlation doesn't necessarily mean causation, so we can't say for sure just by looking at the time series on the basis of correlation, I guess.
Definitely. So definitely. So correlation does not is not the same as causation. That is definitely true. And in fact, we are going to understand that in the subsequent slides. But but still, before going into that, let us look at each of the cases one by one. Say in the first time series, here we see that whenever x is increasing, y is also increasing. Whenever at the same time, whenever y is whenever x is decreasing, y is also decreasing at the same time. So here if I say that whenever that y is the cause and x is the effect, I cannot say that that is necessarily true, but nor can I falsify it so easily on the basis of data. It may have it may, that is it's possible that it is not the case, but at least I cannot show a failing case from this data set. Now if I come to this data set, that so here my claim is that whenever something happens, that is when depending on what happens to y, I can predict what happens to x. That's what I mean by y cause, like y is cause, x is effect, right? So here let us see whether that is true or not. Here y decreased and my claim is that and I saw that x increased. So seeing that, suppose I so on seeing that I make a claim that a decrease of y results in an increase of x, and an increase of y causes a decrease of x. So now I move to the next thing. At t equal to 2 and t equal to 3. So here I see y increased, x decreased. Here I see y decreased and I see x increased. So far so good. So here I see y increased and here I am seeing x also increased. So now I found a violation. Here again I see y increasing. Here again I see x increasing, right? So like it seems that if I like in this case, if I make that statement that y is the cause and x is the effect, then I am running into some kind of trouble. Okay, now but on the other hand, if I try to say that x is the cause and y is the effect, now I can make the claim that there is a lag from the cause to the effect. That is, whenever a change in x takes place, then a corresponding change takes place in y also, but with a lag. That is, so common sense tells us that cause can happen before the effect, but if effect cannot happen before the cause, right? So in this case, the problem what we saw is that probably that when I said that y is cause and x is effect, the thing is like I am considering the like this change at the same time. Now if I consider some kind of lag, let's see then what happens. Here from 150, so there here is a decrease of y, here is a decrease of x. So so I may be tempted to say that I may be tempted to say that to draw this rule that decrease of y causes a like a decrease of x but with a time lag. Similarly, increase of y causes an increase of x with a time lag. Okay, so let us see if that rule is if this is that what I made, the statement which I said just now, let us see whether that holds true or not. So here there is a decrease of y, here there is a decrease of x at a lag. Fine. Again here we see that there is an increase of x, increase of y, and we see that there is an increase of x with a lag. Again fine. We find a decrease of y now, and here we see an increase of x. So my rule gets violated. Right, so when I am even when I am taking the lag into account, then also it is probably not possible for me to say that y is cause and x is effect. But if I now make the reverse claim that x is cause and y is effect, then what happens? So we have already seen that that is whenever x increases, in the next step y increases. Whenever x decreases, the next step y decreases. Here x increases, in the next step y increases. X increases, next step y increases. X increases, next step y increases. So in this case I could not find any exception to the rule. So when I said y is cause, x is effect, I could find a violation. That is, I could actually falsify the claim that see, I have changed y in a particular way. That is, from here to here I managed to decrease y, but still x is increasing. So I probably cannot say, but while from here to here y had increased, and similarly here to here x also had increased. So it seems that sometimes increasing y causes increasing x, sometimes decreasing y also causes increasing x. So probably y is not a cause for x. But if I say that x is cause of y, then because we know that that is a cause can precede an effect. So here we can see that an increase of x is preceded by an increase of y. Decrease of x is preceded by a decrease of y. So if I say that x is cause and y is effect, then at least I am not saying that it is this data set proves it, but this data set is not able to falsify it. But when I had said y is cause, x is effect, then I had actually been able to falsify it. So that is so at certain, although it, as Utkarsh already said, correlation and causation are not the same thing, but in some situations we may be able to rule out certain directions of causality, like in this case. Now let us try to understand the claim once again that correlation and causation are not the same thing. So in this, like for example, here we in this case we saw that there is a high correlation between x and y. Whenever one is increasing, the other is also increasing. Whenever one is decreasing, the other is also decreasing. Fine. So we can, so this does not necessarily mean, although it can possibly mean that x causes y, but it does not necessarily mean the same thing. So for example, like here is a famous example which has been which many people have cited to state this thing. So let us see that the number of suicides in different years in the USA, that is plotted here as this black time series, and the spending on time the space technology in US in different years, that also has is plotted along the with this red line. So here you can see that the red line and the black line are following each other like almost perfectly, right? So like if you actually calculate the correlation coefficient between this black time series and the red time series, you will actually find quite high correlation, say like somewhat close to 1. But so does that mean that one of them is a cause and the other is the effect? Is that even believable? No, right? There does not seem to be any particular reason why either spending on space technology and science and technology will incentivize more suicides, and not does the reverse make any sense. So why is this happening? Any explanation anyone wants to give why such a thing is happening?
Or maybe the scaling of the axis has been done in such a way that the figure fits perfectly. If you change the scaling of the axis, it may very well change.
Okay, maybe that okay, maybe if the scaling of the axes are done in such a way that maybe the time series will not look so close to each other, but even then the general trends that whenever this is also showing a gradual increasing trend. The black one also is gradually increasing and the red one is also gradually increasing, and like besides there are some points where the black one flattens, and at similar points the red one also flattens, and then at some other points both of them seem to be taking off. That is also there. Even if the scaling even if the axis had not been scaled in this particular way, these things would have happened. So then that the point which you made is taken, but that does not necessarily explain the whole matter. Is any other explanation can you come up with?
The population growth.
So what happens with population growth?
So there will be like in general suicides would be more if population is larger, and spending on science and technology should also increase, like maybe.
Right. So yes, that's a better that's a much better explanation. It's what you are saying essentially is that like whether be it population growth or something else also, it's like basically saying that there is some common cause which is driving both of them. That is, it's really there is a there is at least one more time series which we are neglecting to plot, and both the black curve and the red curve are actually strongly correlated with that other time series or those other time series which we have not plotted here. It's like both of these, both the red curve and the black curve, both the spending curve and the suicide curve, both of these are basically the function of something else which we are not observing, or maliciously we are that is not plotting. So why am I not doing so? It may be that I simply do not know. I mean, there are so many variables in the world, there are so many things which I can measure, that is how can you expect me to plot all the things in the world? That is like some kind of a failure or helplessness from my part. That is, I am simply not able to identify all the variables which I should plot here to explain this matter, or I may be working with some malicious intention. That is, I somehow want the funding of science and technology to be cut down, because and for that I am coming up with an excuse like this. I am saying, see, the more you do science and more you spend behind science and technology, the more will there be suicides in the society. So do not spend over science and technology. That's basically this is basically something which we sometimes call as a conspiracy theory, right? Like here we are focusing only on a small part of the data to build up a story which fits a narrative which I am trying to push. Okay, so like the variables which we are not observing but which potentially influences both x and y, these are typically known as the confounders. Okay, it's like confounding means confusing. It's like those variables are confusing me into drawing some strange conclusions. Okay, and these kinds of correlations are known as spurious correlations. It's like an artificially enforced high correlation. I mean, these two time series, there is no reason why they should actually have high correlation, but because they are, both of them are being driven by a common cause, so it turns out that artificially some kind of a correlation is being incorporated between them. Another example might be that the relation between, say, ice cream sales and shark attacks. Say, like, there is a, consider a particular beach, and we see that like in those years where there is the more ice creams are sold on that sea beach, there are also more attacks by sharks. Okay, so based on that, I may be tempted to come to a conclusion that so if I stop selling ice cream on this beach, then there will be no further attacks by sharks. So again, so clearly that's a this is also a spurious correlation, and in this case the confounding variable may be higher temperature. So in those years when the temperature is high, or during those months of the year where the temperature is high, people will obviously want to buy more ice creams, and at the same time the sharks will also get restless due to the warming of the ocean. So they will, in their restlessness, they will attack, they will try to come up to the beach and they will attack people. So in both cases, so in this case the confounding variable is higher temperature, and this is drawing both the x and the y. Okay, so like, if so, the note that if we had considered this as x and this as y, then I would have been, I may have tried to come to a conclusion like this is the cause and this is the effect or something like that, but actually that is not true. The reality is that the cause is this, and both of these are effects of that cause. Okay, so this is the primary reason why we say that correlation and causation are not the same. So whenever we get a time series like this, so from based on the time series we may find high correlation, but that does not necessarily tell us whether there is a causal relationship between those two time series as well. So like as we saw in our earlier example, certain things we can rule out, certain relationships we may rule out, like the one which we did in that previous xy case, but the ones which we cannot rule out are not getting confirmed. If we cannot rule out something, it's not that we have confirmed it. Confirming a causal relationship actually requires lots of more complications. Now let us look at certain examples of economics, which is maybe of more interest in this class. So in our next lecture on Monday, we will see some actual case studies, and I will actually refer you to certain papers. But before that, let me just motivate you with these examples. So how does fertilizer affect crop yields? Okay, so suppose I have a data set which in which I have quantity, I have a variable called x, which is basically saying how much of fertilizer was applied on a particular farmland as a function of time, and there is another variable y which is which is measuring the crop yield from that farmland as a function of time. So let's say both of these are numerical variables. So I may be interested to try to predict y from x. So if at all there is a causal relation from x to y, then I may be then it is possible that I may be able to predict y from x, as we were seeing in the time series case yesterday. That whenever yesterday we discussed about autocorrelation and autoregression. So we saw that whenever a particular time series exhibits the property of autocorrelation, we may utilize the framework of autoregressive or autoregression, or those ARIMA models and so on, which we discussed yesterday. We may use those to make forecasts of the future values of the time series. So here, in this case, instead of focusing on one time series, we may focus on two time series. One is y, the other is x. So here, if at all one is the cause and the other is the effect, then I may be tempted to actually predict the crop yield at time t based on the past values of the fertilizer quantity which I have applied. Okay. But the problem is, can we say that X is the cause and Y is the effect? Okay, so definitely it seems intuitive in this case, and I may actually be able to fit this model also. That is, I may actually, if I try to do this prediction with the help of a regression like this, it's possible that I will actually be able to predict quite well, but still I will not, that will not help me to draw the conclusion that fertilizer quantity is increasing the crop yield. That is to say, if at a so suppose I see that that is, suppose I run this experiment in a particular farmland, and I actually find that using the past values of the fertilizer, I am actually able to predict the crop yields quite well. Does it mean that I can go to some other farmlands also and actually suggest to the farmers how much fertilizers they should apply there to get how much of crop yield? Probably not, because because there are confounders. Whenever in this particular farmland, okay, I may have been able to find a relation between X and Y, but probably there are also some other factors which I did not take into consideration. Some other factors which remained constant through in this, like whenever I did this study and whenever I actually carried out this forecasting problem in the farmland which I am considering, probably there are some factors which remained constant, but they will not remain constant if I move to a different farmland. For example, soil fertility or weather. So it's possible that the farmland in which I tried my model is built on very fertile soil, where anyway, even if we do not give that much fertilizer, then also it's probably would have got a good harvest. Or it may also be due to the weather conditions. It's possible that at the point when I did this study and I got a good result, maybe the weather conditions were enabling, but at some other point of time or at some other place, the weather conditions will not be that suitable. So I will not be able to do the same cultivation. So in this case, although I have been able to fit some kind of a predictive model, in this case a regressive model, it's really I still have not really been able to get a a causal relationship between the X and Y. Okay, another possible example may be how to predict the income which a particular person may make or a family may make. So on what factors does the income depend? Okay, so I may be tempted to focus on the educational qualifications or the degrees which the person has earned or the marks which that person has scored in their different exam, and I might say see a relationship like this: a person who has more degrees or who has scored more marks in different exams tends to earn more. Okay, so this is probably something which we will observe in our data. Okay, and I may actually be able to fit some kind of a predictive model also, which will be able to predict the income of a person based only on their education. But again, does it mean that it's really the X is the cause and Y is the effect? It turns out that even in this case, probably a causal relationship does not hold. It's like one possible confounder might be, say, something like a parent's income. So like if someone has rich parents, then that person will probably get better education. They will, because their parents will be able to fund their education or spend more behind their education, and as a result they will probably be able to study in better schools and maybe have access to internet. They can attend tutorial homes, etc., and hence as a result of that, they will do better in their exams and score more marks, get more degrees, and then they will get better income. or even if they do not like it may happen that even otherwise also, because they are coming from a rich family, they may have better connections, and that's why they are able to get a more high paying job, and hence their income is better. So again, so this is another example why there can be that because we have neglected some confounding variables, I may end up in a simplistic causal relationships like educational degrees or marks scored in exams are the sole drivers of the income of a person. Yet another example might be, how does advertising impact the sales of an item? So in this case, like the two variables I have, X and Y. X is like the amount of money spent by a particular company behind advertising a particular item, and Y is the sales of that particular item in the same place. Okay, so here, same place or in the same time. Okay, so here it may well happen that the data may suggest to me that whenever the advertising is high or whenever or wherever the advertising is high, we see a higher sale of that item. Okay, but then again, can I come to the conclusion that high that the more you advertise, the more you will be able to sell an item? So does it say, for example, does it mean that if I go on advertising, say some winter wear during summer, or if I if I go to some place in Sahara Desert or in Thor Desert and keep on in the middle of a summer and try to sell winter wear, then and if I spend a lot of money in advertising, do you think we will be able to sell winter wear very well there? So probably not, right? So that's because in such places or in such times, the item which I am trying to advertise or sell simply has no relevance. So if there is no relevance, then advertising, the more you advertise, does not mean that there will be a higher sales. Of course, if you are clever enough to advertise in a way that you invent a new use case for that item, so that like even in summer people will be convinced that buying winter wears is useful, then of course you may be able to sell it, but that's a different matter altogether. So in normal circumstances, this will not happen. Okay, so now the question is, so then how, so what I have been telling so far is that causality is difficult. I can find correlations, but that does not necessarily mean causal relations. But suppose I am actually interested in causal relations only. Now, why am I interested in causal relations? For the same reason that suppose that is, if I understand if a particular phenomena is happening and I can successfully identify the causes of that, then I can replicate that phenomena from happening. That is, I can replicate the happening of that phenomena in other circumstances because I know what exactly causes it. On the contrary, if suppose there something bad happens and I am able to identify or pinpoint the causes of that, then I will be able to circumvent that bad incident by identifying all those by preventing all those causes, right? So identifying causal relationships is in importance, and as we will see in the next class on Monday, in the domain of economics also, it is very important. It has multiple use cases. So then typically how do people go about it? So the general way is as follows. So that is, suppose you have you first make a list of that is, you first of all you know what is the outcome which you are measuring, what is the outcome of interest. So like in this case, the crop yield, that is what you are interested in this case the income of the person you are interested in this case the sales of the item you are interested in. So whatever it is, you will have one variable, let's call that variable as Y, that denotes what you are interested in. Now is the set of all possible causes. So you think of everything that may be a potential cause or a potential predictor of that thing, thing which you are interested in. Okay, so it's possible that you like you get a set of 1000 potential predictors for just one outcome, or maybe even more than that. Okay, so now what you have to do, that is so these are all possible causes or potential causes, and the outcome is the effect. So you will have what your task then basically reduces to, out of all these 1000 causes or 1000 potential causes, you will have to identify which are not actual causes and have to retain only the ones which are actual causes. Okay, so now now one way of viewing the causality is as follows. This is something which I said earlier also, is to is to confuse the notions of causality and predictability. So like I may be tempted to say that if I can predict y, the target variable y, from some using a set of potential variables, I mean potential predictor variables x, then I can say that x is the cause, or like the variables in x are the cause and y is the effect. I may be tempted to say that. I mean, I have already shown you why that is not a good idea. But but what I am now saying is that suppose you take so many variables like as your potential predictors, that all the confounders are also included. So here in like when we are doing this problem, here I was looking at only one x and tried to predict y from it, and using that I got a like a spurious relation because there were some confounders. Fair enough. Now what I am saying is that now bring in as many variables as possible as your potential predictors. So that will of course mean these other like confounders also, that is the soil fertility, weather in this case, or the parents incomes, etc. So like if you bring in like as many possible predictors, then you will also have brought in the confounders. Okay, so now once you have done that, once you have taken all possible confounders into account, and then you are able to identify the like a set of predictors which are helping you to predict y, then you may then basically what you have done is you have solved a feature selection problem of machine learning. So those of you who have learned machine learning earlier, those of you who have attended a course on machine learning may be familiar with this concept. How do we do feature selection for machine learning? So there are various algorithms for doing feature selection. One is the like or lasso linear regression. The others is decision trees or random forest. Both of these basically do the same thing. That is, you have a like a large set of possible predictors or features, out of which only a few are relevant. So both these algorithms, lasso linear regression and decision trees, help you to identify the few features which help or a few predictors which actually help in predicting the target. Those predictors which do not play a role in predicting the target are probably not useful. Okay. Now, so this is one way, one possible way in which we can solve the particular problem. So what this lasso linear regression is or decision tree is, those of you who have not studied machine learning will not know. So by the way, so those of you who are not familiar with lasso linear regression or decision tree, at least one of these, can you please raise your hands? Yes. Okay. Janaranjan Pradhan, who else? Okay, 3 hands, 4 hands. Okay, I guess many of you know, but know these concepts, but a few of you do not know either. Okay, never mind. You can take down your hands. Thanks. So, like we will, we will in the next class we will briefly go over Lasso-one decision trees. The thing is that even in the presence, even then, even if we do this particular approach of Lasso linear regression of feature selection using machine learning, then also we may not, we still may struggle in the presence of confounders. So why is that? That I am going to explain to you in a bit. But before that, let's quickly go to look at what linear regression does. So, linear regression is basically something is a technique which allows you to predict the values of a real valued target variable using real valued predictors. Okay, so suppose that the value which you are trying to predict y is a real number, and suppose all the predictors that you are considering x, suppose they are also real numbers, and suppose I have suppose I have some j of them. Okay, so the way we work is as follows. For every example I where I am trying to predict the yi from all the corresponding values of the input variable, what I do is I try to express the predictand variable, the variable which I am trying to predict, as a linear combination of all the all the possible predictors which I am considering. So xij, here I basically stands for the index of the example which I am considering. So I will have lots of observations of the predictors as well as the output variable. So I mean the predictant variable. So let us say this is the ith observation. So the I you can neglect for the time being. It's like saying that this j denotes the predictor which I am talking about, and there are say a very large number, let us say 1000 predictors. So each of their values are denoted by xj, and each of corresponding to each of them there is a coefficient which I am calling as wj. Okay, so as you can see, each of those values I am multiplying by the coefficient, and there is a, like I have kept a constant term also. So basically this is the value which I am predicting, okay, as a linear function of all the predictor values, and yi is the true value. So now the question will arise that how will I choose from where will I get the values of w or b. So these are basically the parameters of my model, and as I was saying in the second lecture, in case whenever you have a machine learning problem like this, you basically have a loss function, you have parameters, and you have a loss function, and you choose the parameters in such a way that your loss function is minimized. So in this case, the loss function is basically the squared difference between the value that you predict, in this case that is denoted by hi, and the value that is actually observed, that is yi. So yi is the observation, the quantity of your interest, and hi is the value which you have predicted for it. So you subtract the two and you take its square. Okay, so I can be, but because your hi, the predicted value can be written in this way. So sorry, the summation, there is a typo here, the summation will be inside. So basically this is the loss function in this case, and then you can actually, like if you have like m data point or m examples like this, you can actually calculate that loss function over that all the users, and sorry, I mean all the examples, and then choose w and b in such a way that this total loss function is minimized. Okay, so how to do that? So like one easy way to do that in this case is you simply get, like you have the expression of this loss function, you know what is the value of y, you know what are the value of the x's, the only thing you do not know are the w's and b's. So what you can do, obviously you can calculate a partial derivative of this loss function with respect to each of the w's. That is, with respect to w1 you do a differentiation and you calculate the partial derivative equated to 0. Why 0? Because I am trying to minimize this, I am looking for a minima of this function. Okay, and because this is a convex function, it will have an unique minima. Okay, so like I will try to calculate the derivative of this thing with respect to W1. I'll get the expression of the derivative, equate it to 0. So I'll get one equation. So again, I will calculate its derivative with respect to W2, equate it to 0, get second equation, etc. So if I have some 1000 variables like this, I will get some 1000 derivatives like that and equate all of them to 0 and then solve the equation simultaneously. So then that will like basically allow me to solve for all these W values, and because of the nature of this function, because it's a linear function, like I will be able to get an unique solution as well. So that way I will be able to assign some weights to each of the predictors. Okay. Now what happens is that once I do this process of linear regression, all the all of these things, all of these predictors, they get a particular weight. Okay, so now, but that does not help my original aim, which is to identify the causal factors, that is to say those subset of the predictors which help me to predict y. Okay, that is so remember that I have considered all possible predictors for y, but most of them are likely to be useless. Only a small number of them should be useful. In fact, I do not want to consider too many predictors. I want to consider only a small number of predictors. Why? Because of the simple reason, too many things or too many factors are difficult to handle. That is the reason I am solving this problem is to get some actionable insights. I want to get some actionable insights. I want to identify which all are the important factors for this variable, and I want to control those few factors only. I do not want to go about changing all variables in the world. So that is why it is very important for me in this case to make sure that that is only a small set of all these predictors are actually selected. Okay, so how do I ensure that? I can ensure that with the help of what they call as sparse regression. Now, sparse regression is such a regression which ensures that out of all, that is all, like I am anyway getting the values of all the w's with the help of by solving this problem. Sparse regression ensures that as many of these are equal to 0 as possible. Okay, so that is why I call it as sparse regression. What is a sparse vector? A sparse vector is a vector where most of the elements are 0, and that is what I want to happen in this case. So if the weight of a particular predictor is 0, that means that predictor is useless for me. If that predictor is not playing any role in predicting this variable of my interest. Okay, so that means what? That means I actually want to, so when I want to select a small number of predictors, I actually want to set most of their weights to 0, and that so that is what I do when I am doing this sparse regression. So the way I go about doing sparse regression is as follows. First of all, the loss function of normal regression is there anyway, which I had decided, which I have defined in this case. That basically helps me to compare the predicted values and the observed values. So this is definitely important. This I still need. Now, in addition, so this is my objective. My objective is to be able to predict y correctly, but it is another of my objective to make sure that the w's are that is the vector of all these predictor weights is as sparse as possible. That means what? That means most of the elements of this w vector should be close to 0. So that part of that is my second objective, that I encode with the help of a function f. And this f function I call as my regularization function. So I choose such a function which takes a low value whenever my w is suitable, and it takes a high value whenever it is unsuitable. So just like in this thing, just like whenever the prediction is good, so this loss function takes a low value, and whenever the prediction is bad, this function takes a high value. Similarly, this regularization function also is something like that. Whenever the W has the property which I want, this F should take a low value, and whenever it does not have, then W should have, then this F should have a high value, right? Now in this case, what is the function or what is the property which I want W to have? That's sparsity. So I basically want to define such a function F on W which takes a low value whenever W is sparse, and it takes a high value whenever W is non-sparse. Okay, so it turns out that there is a matrix norm called the L0 norm which promotes sparsity. So if I choose the function fw as the L0 norm of W, then it actually, and if I am able to solve this problem, then I will actually get a sparse W which also minimizes the error. So obviously the result which I get by solving this problem, this particular problem, and the result which I get from solving this problem will not be equal. This is the like the W I get in this case will give me the least possible error which I can get on Y. So obvious that's a unique minima. So obviously this is if I go for a different W in this case, I will not reach that minima. The thing is that I now want to go as close to that minima as possible while also making sure that I solve the structural property of sparsity. Okay, so it's like saying that among the sparse matrices, which matrix brings me closest to the least value of this error. That is, so many sparse matrices are possible. I mean, many sparse vectors are possible. Give me that sparse vector, which also helps me to predict Y properly. Okay, or as well as possible, right? So now the problem is that if I use this L0 norm of W as my regularization function fw, then this problem, solving this problem becomes difficult. How had I solved the linear regression problem? As I said earlier, we had calculated derivative with respect to W, equated to 0 and solved some equations. I am not able to do that in this case. Why? Because I am not able to differentiate this function with respect to W, as it is a non-differentiable function. In fact, it is a non-continuous function also. Right? So what I have to do? I have to, instead of using the L0 norm, I use what is known as the L1 norm of W, which is nothing but the sum of the absolute values of the elements of W vector. Okay. So what this does is, if I had solved this problem, then I would have got a sparse W. In this case, I will not get a sparse W, but I will get an almost sparse W, which means that most of the elements of W are close to 0. Okay, they may be something like 0.1 or 0.5 or 0.05, something like that. Not exactly equal to 0, but small values. So that I can now define a threshold and filter out all the values which are close to 0, and I can say that those factors are not useful. Okay, so that is the way I do what is known as lasso regression. Now the problem with this lasso regression is again the same, confounders. So why are confounders coming in here? That is because some of the predictors which we are choosing in this case, some of those predictors may influence the other predictors. So suppose like in this case there were my initial set of potential predictors comprised of some 1000 variables. Now I apply lasso and I get an almost sparse W, which means that most of those 1000 potential predictors have low coefficients. So most of them I filter out. Say I am left with only some 25 predictors now. But the problem might happen that those 25 predictors may again influence each other. It may happen that there are some 15 predictors out of those 25 which actually influence the other 10. So still we have not been able to get rid of the confounders. When we are talking about only in terms of machine learning or only the prediction problem, then yes, the lasso may actually help me to like identify a subset of predictors while also enabling me to do good prediction. But in this case, when I am talking about economics, then or causality, then I am not satisfied with just that. I want, like, I not only want a small set of predictors, but I actually want causal predictors. I want those predictors which I can actually call as the causes of the target variable y, which I am looking for. So for that, it is important for me to get rid of the confounders also. Okay, so that is why they do what is known as the double lasso problem. So double lasso is something which is like, it's called a two-stage lasso. It's like first you express, so the steps are as follows. So you have the huge pool of potential predictors, say 1000 predictors. Now you fix one of them as a possible treatment. You somehow narrow down your focus on one of the predictors. Okay, so and the other of the like the remaining 999 predictors, you can consider them, or you can like club them together as your x. Okay, like as your x variable. Now what you try to do is you try to formulate your regression problem in this way. That is to say, the target variable y is still being used as a linear combination of all the things, but I make a distinction between the di, which is my my treatment, and xi prime, which is basically all the predictors except the treatment. Okay, and so I formulate this as as one part of the regression problem, and then I formulate another regression problem where the treatment itself di I try to predict with the help of all the remaining things. So that if there are some confounders, the confounders should basically like this will enable me to identify which are the confounders. That is, from if there is some confounder, that is to say, apart from the treatment di, if there is some other variable which is influencing di also and yi also, then those, like when I solve both of these problems simultaneously, then I will be able to identify those confounders. That is, I will that is solution of, when I apply lasso on this problem, I will some of the variables in or some of the predictors in xi prime will get selected along with di, which will of course be selected. Similarly, when I am when I am solving this problem and applying lasso on it, then again some of the predictors from xi prime will get selected. And now I will specifically see, is there any overlap between the predictors of di and the predictors of yi? If there is, then basically those are my confounders. Okay, so that will enable me to understand that which variables are the confounders, that is, they are impacting both the treatment di as well as the outcome yi, so that I can so that whatever analysis I want to do after that, I can take them into account. So this is one way in which, so the thing is, lasso itself helps me to do feature selection and prediction, but it does not help me to identify causal relationships, because because it cannot separate out the confounders. But if I do double lasso, then it helps me to identify the confounders as well. And so then I can actually identify that so then if I am interested to answer this question, that is the control variable di, is it a causal factor of yi, yes or no? So if I do this double ML, then I will probably be able to answer that question. Okay, so it may turn out that when I am solving this problem, di, that is the impact of, that is either the weightage of this alpha naught, or the coefficient of this di is quite low, or if not zero. That will mean that this di is not actually playing a big role in predicting yi, but some other things are. and it may I may also find out that those other things, some of those other variables are actually helping to predict DI. So that means that there are that DI is actually not the cause of YI, but rather there are some other confounding variables which are driving both YI and DI. So that I do not reach conclusions such as the suicides in US are causing the increase of spending in science and technology, or that ice cream sales are causing shark attacks or something like that. Right, so that like this will enable me to identify the confounders and actually solve the causality problem. Okay, so yeah, so let me stop here because we are past time. So in Monday's class we will like discuss more about this idea. We will actually consider a few use cases of related to economics, where we will see how this concept of like identifying these causal relationships or identifying these confounders are used using this new algorithm which we studied, which is of this double lasso. Okay, so we'll continue this on Monday.
Thank you, sir.
Thank you.
Thank you. Thank you, everyone. So like if you look at the folder, you can see that I have shared these lecture notes. I have also shared certain research papers and presentations by some other universities, where some of those case studies which I mentioned are presented. So I request you to go through some of them before the next class. I will not be able to cover all of them in the next class. I will some of them I will cover, but I request you to go through all of them, and your assignment too may be on the basis of some of these things.